Good morning, everyone. Thank you for being with us today. I'm Eamon Benazi. I'm a member of the programs team at the Society of Petroleum Engineers Young Professionals, and we're very excited to be hosting this event today in collaboration with the Petroleum Technology Alliance Canada and the Canadian Academy of Engineering. I've had an opportunity to chat with our speakers over the last few weeks at some point or other, and let me say, we are truly honored to have such amazing and dedicated people volunteer their time to share their knowledge. The topic we've brought today is one that will take on a lot more significance in the coming years and decades, and is a source of hope for our generation and future generations. Before I pass it off to Suhail, I would like to take a brief moment to thank the SPE YP sponsors for helping us bring these events together, where we get to learn about new topics and hear from subject matter experts, as we are today. We'd like to thank Chevron, Hexion, Geologic Systems, and Avintiv for their continued support for all of our programs here at SPE YP. We now look to Suhail to provide us with a few more details on the housekeeping rules, the topic, and our speakers. Thank you, everyone, and I hope you enjoyed today's event. Suhail, over to you.
Good morning, good afternoon, everyone. On behalf of the Canadian Academy of Engineering and PTAC, it is my pleasure to welcome you, the CAE Fellows, members of other academies, and SPE members, and also students to this webinar on nuclear, fission, and fusion, widening the path to net zero. My name is Sohail Askarpour, President of PTAC and President-elect for the Canadian Academy of Engineering. This event, as you know, is actually the third event that we have in a series dedicated to net zero emissions to discuss the common challenges Canadians face with meeting this difficult target. Of course, you know that this target is by 2020. And of course, this is all about how collaboration and innovation can get us closer to achieving this target while maintaining Canada's economic prosperity. You can view the presentations and video of the first two webinars on the Academy's website to inform our students and members of other organizations who may not be familiar with the CAE. The Canadian Academy of Engineering is the national institution through which Canada's most distinguished and experienced engineers provide strategic advice on matters of critical importance to Canada. The Academy is an independent, self-governing, and not-for-profit organization established in 1987 and is one of the three national academies that make up the Council of Canadian Academies. We have over 800 fellows from across Canada, all of whom have made significant contributions to engineering in Canada in the private, public, and academic sectors. I should mention that the views and opinions being expressed here are those of the speakers and myself and do not necessarily reflect the official policy or position of the Academy, PTAC, or SPE, and they are only for knowledge sharing. Having said that, the Academy has identified the net zero target by 2050 as the top priority. The Academy has engaged many fellows and is in process of forming a task force to evaluate and assess various pathways completed by various organizations in achieving net zero by 2050. If you are interested in joining the task force or participate in providing your expertise, your talent, please contact me. The webinar series is the main tool for broadly disseminating the learning from the work of experts in this field. So far, we have discussed the challenges of the net zero at high level and assessed the option of electrification and electric cars. Today, we will talk about potential contribution of nuclear fission and the future opportunity of fusion. In the next webinars, we will assess solar, wind, biofuels, oil and gas, hydrogen, smart homes, CCUS, methane, energy efficiencies, etc. Before we get started, I would like to go over a few housekeeping items and explain the format of our online proceedings. If you have a question anytime during the presentations, we invite you to use the Q&A option, which is at the bottom of your screen, and we will do our best to get your questions answered. For more information, this session is being recorded and will be available on our website. We have 3 presentations for you today on fusion, emerging nuclear technologies, and small modular reactors, SMR, which will be delivered by our 3 distinguished presenters. After the presentations, I will open the floor to answer your questions. Finally, I will ask each panelist to provide their concluding remarks for 1 minute. Now, let's get started with my own remarks. Nuclear is key to clean energy transition. New and emerging technologies provide the opportunities to generate safer electricity, heat, and hydrogen at near zero emissions. About a decade ago, we at PTAC launched 4 phases of a study to assess the application of nuclear technologies to generate steam, electricity, and hydrogen for in situ oil sands operations, mainly for SAGD, steam-assisted gravity drainage. The first phase was about the assessment of water-cooled reactors. The study concluded that water-cooled reactors cannot provide the requirements of high-temperature steam for SAGD. The second phase of the study concluded that high-temperature gas reactors can meet the requirements for SAGD. For the third phase, we invited the nuclear power plant owners, technology providers, and producers with the goal of forming a consortium to work together. We created a non-binding term sheet. The oil sands operators indicated their wish to explore the option for buying steam, hydrogen, and electricity over the fence. The nuclear power plant owners wanted to see direct engagement of producers in the operations of nuclear. So the negotiation failed. The fourth phase was to find a solution to use much larger reactors. Essentially, we wanted to reduce costs. We collaborated with Idaho National Lab, and Phil will discuss the innovative ideas that we actually work together on. Our presentations today will start with a broad business application and value proposition of nuclear energy and its possible role in achieving net zero. Then we will dive into SMR and finally discuss future of fusion. So on that note, I would like to introduce our first speaker, Mr. Philip Hildebrandt. Phil is a special assistant to the laboratory director, Idaho National Laboratory, and that would be for major projects, industry, and regulatory strategy. He has over 50 years of experience in the nuclear and power generating industries. His experience has been gained through a wide range of engineering and management assignments in the Naval Nuclear Propulsion Program and in commercial nuclear power plants. The experience has included senior management roles and consultation to commercial power generating companies and utilities, and government contractors in various project management and engineering management of reactor facilities and other nuclear chemical facilities. Phil has worked closely with senior and executive management within power generating companies and utilities, as well as the Nuclear Regulatory Commission, the Department of Energy, the Department of Defense, and the Department of Commerce. So with that, please join me in welcoming Phil to make his presentation. Phil, you have the floor.
Well, thank you very much, Neil. And again, good morning or good afternoon, wherever you may be. I welcome the opportunity to give you an overview of the possible future of nuclear energy as part of achieving net zero carbon emissions for energy production. Next slide, if we could, please. And I'm going to focus the discussion around the overarching business considerations in achieving net zero carbon emissions. And it primarily reflects the energy producer. And how does that differ, perhaps, the way that the structure of energy producers in Canada? I think it's primarily from the standpoint of how business risk is approached and the extent to which government help set the agenda for corporate decision making. But other than in those areas, I believe there's very similar and parallel thought processes in what the overarching business considerations are going to be. I also take a look briefly at nuclear energy system options, and these are fission options. I'll let Axel talk about fusion. I'm not qualified for that discussion. I'll look for some major challenges in nuclear energy, what it's really the hurdles that have to be overcome. Discuss some of the energy production and transport technologies and how we might choose them, and then give some examples in the three areas that are listed on the slide. Next slide, please. Now, this is a list, and I won't read it to you. This is a list of some overarching energy production business considerations in transforming to net zero. I'll focus on a handful of these. One, looking at competitive energy production costs. Two, the reliable energy production. How do we get to an acceptable business risk from the perspective of an energy producer? And then lastly, looking at, for electric power systems specifically, what are the thought processes in getting to a diverse energy production portfolio? This is clearly a discussion of not just nuclear energy, but what is the mix that makes sense? Next slide, please. In terms of nuclear energy system options, fission reactors in particular, there's a broad array, more than you can shake a stick at, that currently exist out there in the industry. And they won't all survive. That's just part of the business of finally down selecting to what make the most sense from a business standpoint. And understand, I am approaching this from a business perspective, not from a technology perspective, because the companies, particularly investor-owned companies in the United States, look at technologies and hopefully, to the extent they can, on a level playing field, and make their decisions based on business decisions. Technology is not the driving thought process. So what are the options? There are a broad range of options available. The existing large light water reactors and heavy water reactor designs in Canada that have been deployed. The evolutionary light water based small modular reactor concepts, which are being looked at very closely both in the United States and in Canada today. and some alternative reactor coolant that are not water-cooled based small modular reactors, and some larger reactors as well. Now, these evolutionary and non-LWR technologies are interesting. They're not all new thoughts. Many of these we've looked at over the years, as far back as in the 50s. And these are variations on the theme that were looked at in the past, and with a great number of improvements associated with it. So, some characteristics that are important. One, there's a higher operating temperature available in most of these designs to support industrial process heat applications. Very important option as an alternative business application. The extent of nuclear safety is often intrinsic to the technology and design, reducing the potential for operating events and dependence on external systems. I'll come back to that item a little bit later on. And there are alternative fuel cycles, uranium, thorium, open and closed cycles, a number of different approaches to how we employ and deploy the nuclear energy system. Next slide, please. Now, if I look at the United States, and I'll focus because that's where most of my experience is, and I share this with you. Nuclear energy development in the United States today is very broadly based, not focused on bringing any particular concept to commercialization today. We're looking at multiple different options. Our major US electric power producers are committed to decarbonization. These are the folks that have been the owner operators for nuclear energy systems in the past. But that is a work in progress. What the role of nuclear energy is yet a work in progress. The planning is yet to be finished, if you will, or even hardly started in many cases. And what is the role of nuclear energy? In part, it's waiting in major part by the policies of the United States government as to where we're going with our net zero carbon emissions policy. What is it going to be? What's going to be the structure that will be enshrined presumably in legislation in our Congress? And what's the timing for that? You may have seen that in the public media, where the current administration is pushing towards 2035 date for achieving net zero in the electric power industry, whereas the power industry has been looking at 2050 in general. Now, just as a brief summary of ongoing nuclear energy system development enabled by the US government, and this is in partnership with the private sector. There's first the NuScale SMR, the carbon-free power project, so-called, the cost-shared development and first-of-a-kind development activity. The Advanced Reactor Demonstration Program. It's a federal cost shared with private industry, 50-50. And it's looking at two medium-term demonstration projects. One's a gas-cooled reactor, the X-Energy HTGR, a high-temperature reactor. You can look at the previous slide and get an idea where the temperatures are. And the TerraPower GE Hitachi Natrium sodium-cooled reactor with integral energy storage. And those are the starting point for our demonstration projects, claim to be operational in 7 years. I think that will be a stretch, but claim to be operational in 7 years, and intended to form a foundation for where we would step off into application of advanced reactors. If that should fit the business case for the energy producers. And there are five longer term potential demonstrations, which I won't read to you here. You can look at those, and there's plenty of public information available. We also have a microreactor program, which is focused on enabling research and development, deployment, commercialization of microreactors for non-conventional markets, remote communities, mining sites, remote defense bases, which is parallel to activities going on in Canada at the present time. Next slide, please. Now, what are the major challenges for nuclear energy? One is, and probably the most difficult one right now, is demonstrated economic viability. We've had a number of false starts over the decades in terms of achieving economic viability of nuclear energy. Our recent experience with the Plant Vogtle Units 304 in the state of Georgia got off to a bad start. It's an example of how not to build a nuclear plant. They began construction well before the design was done. And they've run into a number of problems over the life, and they'll finally be operational over the next couple of years, but a real challenge, and hence not a good demonstration of economic viability for a large so-called stick-built light water reactor. Now, the small modular reactors have the potential for lesser capital investment due to factory modular construction compared to the economy of scale of the large light water reactors or other technologies. It doesn't have to be an LWR, but that's not yet demonstrated. And I hope we're able to show that that comes true. However, it's not demonstrated at the present moment. Also, from a standpoint of economic viability, is the grid compatibility. The large LWRs require a large compatible grid. It's not something you'll put in a small isolated grid or in a remote location. SMRs, small modular reactors, can fit better in the smaller and variable size grids. Hence, there's an advantage, particularly when we're dealing with isolated grids or small grids. The other major challenge is the high-level waste disposition pathway. And this is the hurdle here is primarily political and societal. The technology is understood. How we should characterize a site is understood from our perspective in the United States. We understand how to approach this. However, we have yet to overcome the issues from a political and societal standpoint for the acceptance of long-term storage, and I won't call it permanent storage, long-term storage of high-level waste. Next slide, please. Now let's talk a little bit about choosing energy production and transport technologies. And again, I'm doing this from a business perspective. I'm sitting back and saying, as I look at options, what's the best one that fits my business model and the approaches and the business lines that I have? So what's the expected energy utilization? Which lines of business do I want to be in? Historically, US utilities and power generating companies have been in the electric power business. That's what they do with nuclear energy. However, there's the opportunities opening in the areas of hydrogen production, the potential for process heat for industry, such as was mentioned by Sohail for the oil sands. And there's a hybrid energy production utilization where we look more broadly at the combination of electric power generation and process heat production in combination with a number of different off-takers and build a business model under the case of multiple off-takers. So questions like, what is the proximity energy production to where energy is used? As I'll discuss in a few moments about the oil sands, we're talking about kilometers between where the energy source may be and where it's utilized. How do we move it? How do we transport that energy? Electrical transport is one way to do it. However, that brings some inefficiency problems. Steam is another, molten salts. So how do we move it from where we generate or produce the energy to where we want to utilize it? A different question than we have faced in the past when it's been electric power generation as our sole business. And what's the capability for accommodating changing energy markets? I use the specific example here of how the energy market may change over the next 3 to 4 decades as we go towards net zero emissions, as we change how we handle the transportation industry, for instance, electrification, how we might utilize hydrogen, how do we get to the net zero carbon emissions marketplace, and then how does it change over time? So what's the capability for accommodating the changing energy markets as we go through that, since it will not happen overnight? And the next 4 slides summarize 3 notional examples for nuclear energy. One is electric power generation. Second is hydrogen production. The third is the cogenerator process heat and electricity in the oil sands example. Next slide, please. So let's look at a diverse production mixes for electric power generation. What's the optimal mix? There have been many regional and system level studies that are done. I mean, you can go to your bookshelf or online and find a large number of them. They all come to the same basic set of conclusions, that the optimal mix is a function of legacy and anticipated future resource options, no surprise. A cost-effective, reliable, and decarbonized grid requires firm capacity, the old terminology, base load. There needs to be a considerable amount of firm capacity. A broad range of technologies, and I'm not speaking here just of nuclear, but a broad range of production technologies lowers the cost and business risk, and I'll discuss that in a moment. Power producer considerations. Now I've gone from energy producer to power producer here because we're looking at electric power generation. That are most often missing in these studies are the things that are listed there. How do we deal with stranded assets? What are the business lines of interest to the power producer? What's the corporate appetite for risk? And that's probably the one that overwhelms all the rest of these. How much risk are the power producers willing to take? Are they willing to build, as the expression I often use, are they willing to bet the farm? Investment in this transformation to net zero is going to really cause, at least in the United States, which is primarily investor-owned power generation, a real struggle for how much of the corporate wealth we're going to bet on the transformation and to what extent the government may be asked to help. And of course, and the last one on that list is the state and regional policies and politics, of which we have at least 50 different versions of that. So that, and you have fewer of those, but you have the same challenge. On the next slide is an example for New England. Now, this is out of a study that was done by MIT, the Future of Nuclear Energy in a Carbon Constrained World. And I offer that you may want to look at that directly. The figures may be difficult to see on these slides. But what's the bottom line out of this? The bottom line is if you try to do it with singular technologies, or what is currently popular in New England, which is where I live, is, gee, we want to do it all with renewables. And what that does is drive the costs way up. The issue is there's a better balance. And what this study did was take a look, it opened the door and it said, what are the possible options as we decarbonize where we should combine different technologies for generation and production of energy? What seems to be the best mix? And what kept coming up, and this shows it for New England, but the same thing's true in Texas and other places where this study looked, it keeps saying nuclear energy is a very important contributor to successful net zero emissions, decarbonization, as you go to the right in those figures. As you increase your decarbonization, nuclear energy plays a larger and larger role to achieve best overall costs for production of energy. Next figure, please. Another area, nuclear produced hydrogen. And I've just borrowed here from the International Atomic Energy Agency and out of their toolkit. And there's a large potential, but it's a work in progress. We're looking very hard in the United States at the use of water electrolysis in conventional use of power off the grid or directly off of a light water reactor. But that business case is limited. That business case won't carry you forward into the future, where you're having to build new infrastructure, and in particular nuclear infrastructure, where over 70% of the costs of the initial capital investment and the eventual production costs are that capital investment. I'll repeat that, over 70% of the production costs of a nuclear facility are tied up in the capital investment. So it's very important that we look for ways to get to higher efficiency nuclear produced hydrogen, for instance, areas like high temperature steam electrolysis and some thermochemical cycles. Next slide, please. This is the one that Sohail mentioned and promised early on that I would touch on. And I apologize, the figure is very difficult to see on a slide. And the reference to the report is at the bottom of the slide. And I encourage you to go take a look at it. The report is public. And this was a look at how we might take high temperature gas reactors as the source of electricity and process heat for the SAGD operations and the oil sands. And the concept we came to jointly with PTAC, and this is with the Idaho National Laboratory and PTAC working collaboratively, was a central energy facility, the thing in the center of the figure, the HTGR facility, so-called, which will then provide steam and electricity up to 25 kilometers from the HTGR facility to what we size as 20 well pads simultaneously, assuming 10 well pairs per pad. And we also included a 145,000 barrel per day syncrude upgrading process. We factored in a considerable bump factor, if you will, for the construction in remote locations. So the economics are based on that increased capital investment. The bottom line, over 60 years of operation of the centralized facility with moving from well pad to well pad in terms of moving energy by steam in this case. If you read the detail, you'll notice it says that steam in supplying the energy to the well pads as well as electricity. At the time this work was done, natural gas prices were plummeting downward, and the economics didn't look very favorable. But the box at the left is interesting. For a natural gas price, which CAE has estimated at $4 per gigajoule, and a carbon tax of $170 per ton, these are in Canadian dollars in 2030, combined with some anticipated capital cost reduction for modular designs, this notional concept may be economically competitive with natural gas. And it suggests a closer look may be warranted. And I'm suggesting here that Sohail and others may want to return to this discussion again with the projections for the carbon tax and what advantages we may get out of small modular reactor designs over time. That could say this might be an economic choice that we should look at very seriously again. Let me go to the conclusions, please. Next slide. Nuclear energy does provide a compelling option for clean, economic, reliable energy production. And there are multiple potential applications that range from electric power generation to process heat production for industry. We have a lot of choices. Water-cooled and moderated reactor technology, some of which are applied in the small modular reactors, have extensive good operating experience, over 19,000 reactor years. The accidents and events that we have that have occurred are not technology oriented. They're a result of design flaws and misoperation. And those of you who may be interested in talking about that in more detail, I would suggest a separate conversation, because folks tend to assign what occurred to a particular technology, and it's not. It should be assigned to the specifics of the design, where the flaws were, and how they were misoperated. Emerging evolutionary and advanced systems offer the potential for reduced capital investment. Very important. And better matching of production capacity to the application. And I underline this next point very strongly. All nuclear energy technologies will fulfill the acceptable yardstick for nuclear safety imposed by the regulators, or they won't be licensed. Shouldn't use safety as the reason for choosing a particular technology. the choice ought to be based on the energy need and the capability to produce what you want economically. We ought to choose the options for maturity and commercialization based on the energy producer's choice. And I'll repeat this, the demonstrated economics will define the future of nuclear energy, not a perceived safety case. Underline that, the demonstrated economics. And we have still quite a hurdle to go before we have done so, but I'm optimistic we can. Thank you very much.
Phil, that was an outstanding presentation, very thought-provoking and well-informed. So thank you very much. We appreciate that. The next presenter is Mr. Ali Siddiqui. Ali is the head of Directorate acting for the Advanced Reactors Directorate at Canadian Nuclear Lab. Ali has a range of management and leadership experience gained through roles including leading CNL's thermal hydraulic experiments and analysis group, corporate manager, supporting the executive team in the office of the CEO over the period spanning AECL, CNL restructuring, and in program management roles with essentially diverse range of research, including the nuclear fuel and SMR. His current accountabilities as the acting head of directorate, including leadership of over 150 scientists and technologists, management and oversight of diverse set of advanced reactors related federal and commercial research projects, strategic planning, development of new S&T opportunities, and support for the SMR projects at CNL. So with that, please join me in welcoming Ali to make his presentation. Ali, you have the floor.
Thank you very much for that introduction, and it's a pleasure to be here today to talk about one of my absolute favorite subjects, which is SMRs. So let's get going. Just a couple of words about the organization I represent. Canadian Nuclear Laboratories is Canada's national lab focused on national priorities. We are Canada's national nuclear lab with a diverse team of over 3,000 staff and a laboratory located at Chalk River, about 2-hour drive west of Ottawa, and project sites across the country. Our campus at Chalk River houses 50 plus unique laboratories across a range of different capabilities, nuclear fuels and materials research, radiobiology, hydrogen and isotopes research, nuclear safety, security, systems and engineering, and nuclear chemistry. As a Canadian, I'm very proud to say that Canada is the second country in the world to harness nuclear fission. And it's important to note that that was way back in 1945 with the ZEEP reactor, which is not far from where I live here in Deep River, just at Chalk River Laboratories. And this was the first critical facility that went critical outside of the United States and really shows that Canada's been a leader in nuclear technology ever since its inception. Over the years, CNL, as Canada's national nuclear lab, has been involved with the development and research across a range of different small reactors. So as much as small modular reactors are new, they've also been around for many years, and they're gaining renewed interest for many reasons, which I'll dive into a little bit more. Throughout the decades, these reactors have enabled groundbreaking innovation across energy, health, material science, and much more. CNL's missions are threefold: to restore and protect the environment, clean energy for today and tomorrow, and to improve the health of Canadians. And SMRs and reactor technologies really fit under the clean energy for today and tomorrow. CNL's vision for SMRs is to demonstrate the commercial viability by 2030 and be recognized globally as a leader in prototype testing and S&T support, and really have a location where multiple supported prototypes are built and tested. So the idea here, small modular reactors, it sounds simple. Small refers to both the size of the reactors themselves as well as the energy output, anywhere from several hundred kilowatts up to 300 megawatts electric. Modular refers to both the construction and operation. So the intent would be for factory produced modules to be transported to the site and assembled somewhat like Lego blocks. Operators can also attach multiple modules to get larger power output depending on changing energy needs. And these are fission reactors utilizing nuclear fuel and related materials. These designs, however, are aimed to be smaller and more cost effective than contemporary reactor designs. SMRs really are an opportunity for Canada to decarbonize, and in particular, in areas which would be very difficult to decarbonize with other technologies. They really are the next great opportunity for Canada to reach net zero goals by 2050 and ensure economic growth and provide energy for all. Canada is in an excellent position with partners around the world to lead in SMR deployments. I would point to a couple of particular notable framework agreements that or documents that came out in the last year, including Canada's climate change plan, Canada's hydrogen strategy, and Canada's SMR action plan, all of which lay out a future that includes nuclear and SMRs. There are many markets for SMRs in Canada, and I'll talk a little bit more about that on the next slide, but certainly in sectors such as oil sands, in mining, in heavy industry, remote sites, and as a replacement for coal-fired generation. SMRs look quite promising. And they can be used to produce steam, process heat, electricity, and even be applied to produce hydrogen to use energy in the most efficient way possible. I want to give you a little bit of a picture of the SMR landscape as it sits today. And I guess it's worth really highlighting here that in Canada, there really is a coordinated national effort. From a federal perspective, I've mentioned some of these framework documents, including the SMR action plan, where over 100 organizations have laid out something like 500 specific actions moving the SMR agenda forward. In the climate change plan, the Minister of Natural Resources specifically called out nuclear to help achieve 2050 climate change goals as zero emission goals by noting that there really is no credible climate change plan to reach 2050 targets that doesn't include nuclear. And I think that's really critical, and SMRs are an important part of that. From a provincial perspective, the provinces in Canada are the ones that actually set energy policy. And so they have a critical voice to play and a critical stakeholder here. There's a provincial memorandum of understanding that was signed by 4 provinces, Ontario, New Brunswick, Saskatchewan, and Alberta, that defines a pan-Canadian approach to SMRs. In this document and in the associated work done by the utilities in these provinces, there have been 3 streams of SMRs identified in Canada. Stream 1 is on-grid replacements. Stream 2 would be on-grid advanced reactors that are a little further out in terms of technology development and may come online in the 2030s. And Stream 3, which are off-grid microreactors. It's expected that a strategic plan will be issued by the provinces at some point very soon. From an industrial perspective, utilities in Canada are working with SMR developers. The established nuclear utilities in Canada, including Ontario Power Generation, Bruce Power, and New Brunswick Power, all are working with SMR developers to evaluate designs and move engineering and design work forward. There was recently a utility SMR feasibility study that was released just in April that laid out many of the benefits of SMRs in the Canadian context, really focusing in on jobs, GDP growth, and the fact that to reach climate change goals, it would be more costly to do so without nuclear. I would encourage everyone to check that one out. I also want to highlight in particular that CNL, as Canada's National Nuclear Lab, is helping SMR deployments by setting up a siting invitation process. I'll talk a little bit more about that in a moment. There have also been some exciting recent funding announcements for SMR developers through Canada's Strategic Innovation Fund. I've already noted the many applications, in particular for heat and electricity that SMRs provide. And this really provides an opportunity for sectors such as mining, oil and gas, and others to reach decarbonization goals. This slide is taken out of the 2018 SMR roadmap, and it really does a good job of giving a quick snapshot of some of the potential markets for SMRs in Canada. Oil sands are a very attractive area where there's huge requirements for energy, where SMRs can play a role. I've already mentioned high temperature steam for heavy industry and potential for mine sites or remote communities. R&D and innovation are critical to realize the full potential for SMRs. And CNL is really looking to accelerate the deployment of SMRs by working out first-of-a-kind issues. And there are many opportunities where CNL as a national lab is involved. So I've mentioned enabling a demonstration. This is really crucial. And this is important to help further enable licensing activities of a first-of-a-kind unit, creating an intellectual property, developing spin-off technologies. And of course, as a national lab, we have a role to play to entrench knowledge in Canada and grow our skills and the skills in Canada with human capital. We have several enabling components to help CNL achieve the vision that we've laid out to see SMRs come to fruition in Canada. Notable components here include our federal science and technology program, enabling us to build capabilities and support the federal family for science-informed regulation and to inform policymakers. Canadian Nuclear Research Initiative, which is a cost-shared research program that enables SMR vendors to access CNL's capabilities in a collaborative approach. Cedar Park, which is our clean energy demonstration, innovation, and research park. I'll talk more about that in a moment. And really critical is this SMR siting initiative that we have at CNL to see our SMR demonstrated on a CNL managed site by 2030. I'll give a few more comments on each of these before moving on. Federal S&T, this is the sort of backbone of what we do at CNL for work for the federal family or the federal government. We have a broad array of different research projects on the go across a range of different SMR technologies, including molten salts, high temperature gas reactors, development of advanced codes and modeling capabilities, new test facilities to better understand and further generate data to validate models, and advanced fuels and fuel cycles. This is just the tip of the iceberg on this slide, but as you can imagine, there are many different technology solutions that have to be developed to better understand and inform regulators for these new technologies in Canada. Our Canadian Nuclear Research Initiative, this is a collaborative R&D program to support research on SMRs at CNL. The goals of this program are to support the development of technology and connect vendors to CNL's unique capabilities, accelerate the deployment of SMRs to achieve all the climate benefits that we're talking about, and achieve CNL's vision to become a global hub for SMR research and development. We launched this program just in late 2019, and in the first full year of the program, we completed 4 projects for the following vendors: USNC, Kairos Power, Moltex, and Terrestrial Energy across a range of different topics. This was really valuable for both the vendors where we're doing research with them, but also for CNL to better understand the questions and technical gaps that still need to be solved. Year 2 of the program was launched in late 2020, and through the winter, we received strong response. Negotiations are underway right now with several vendors, and we expect some announcements soon on new contracts. So this is a very exciting area, and it's nice to be working directly with SMR vendors commercially to move their work forward. In addition to scenery, CNL has started to develop a plan for a clean energy development, innovation, and research park. The goals of this research park concept are to leverage prospective SMR at CNL and demonstrate coupling to low carbon technologies in a nuclear renewable hybrid energy system. The idea here is to develop this SMR in tandem with a nuclear renewable system with energy generation, storage, and energy applications. To date, we've performed a preliminary market survey and a business case study. And at this stage we're at now is a marketing evaluation, developing client requirements, and an engagement plan. The role of building an SMR demonstration project is really crucial. And there's real learning by doing that is critical to realize the full promise of SMRs in Canada. Several opportunities exist. As Canada's national lab, CNL is right in the position to help further these opportunities in Canada. Of course, the first on the list is technology development, and that's really what our scientists and engineers work on every day. But of even higher importance to society more broadly are proving out the economics of SMRs and social acceptance. There's a real value in building a demonstration project to allow communities or utilities to come and kick the tires and see these technologies actually deployed and working. Building up expertise and familiarity in the regulatory process is another important enabler, as well as all the other benefits you expect from these large projects: job creation, IP, development of a robust and sustainable supply chain, innovation spin-offs, and of course, economic advantage for early movers in this new area, both within Canada and anticipated deployments of SMRs around the world. CNL's demonstration timeline is moving forward quite rapidly. With the initial concept and a request for expressions of interest starting back in 2017, we launched an invitation process and first intake of applications in 2018. In this first intake, we received several applications. Throughout 2019, CNL furthered a development of potential sites and performed environmental baseline studies. We actually have multiple sites available at both our Chalk River Labs location and at a site that we have in White Shell, Manitoba, that may be suitable for SMRs to prove out their designs. We have some first agreements in place, which is very exciting. I'll talk about on the next slide, with one particular vendor that's moving forward rapidly within our process. And we're basically on the trajectory to demonstrate first power by 2030. So it's an exciting time. The latest news on our invitation process, I've pictured here the logos from the 4 vendors that have formally entered into our siting process at CNL. One applicant, Global First Power, which is a joint venture between Ontario Power Generation and USNC, has submitted their application to the Canadian Nuclear Safety Commission for a license to prepare site at Chalk River Labs. They're currently in stage 3 of our process, going through negotiations. This is the reactor project that's actually the furthest along in Canada at the moment and is very exciting. This is a small high temperature gas reactor. The other 3 proponents that are listed here have completed their pre-qualification stage. We are hopeful that additional SMR vendors may enter our open siting process over the coming years, as we still have plenty of room at our sites. So CNL is always looking for highly motivated and talented individuals, and we absolutely anticipate a lot of growth in SMRs and other exciting nuclear research. So I'd encourage you to check us out on our website. It's been a pleasure to give you this overview of SMRs in Canada. Thanks very much.
Thank you very much, Ali. This was a very good presentation, and I think we really hit really important items that we can discuss at the Q&A. Next presenter is Dr. Axel Meisen to talk about the status of the fusion technology challenges and opportunities. Axel advises boards and senior management in Canada and abroad on strategy development and implementation of major initiatives with long-term time horizons. Examples are projects on bitumen beyond combustion. This is a project to convert bitumen to value-added opportunities such as graphene, etc. Solid waste management in the Capital Regional District of British Columbia, and environmental technology and management in Saudi Arabia. Axel held the inaugural chair in foresight at the Alberta Research Council after serving as president of Memorial University of Newfoundland, president of the Canadian Commission for UNESCO, and Dean of Applied Science and Professor of Chemical Engineering at the University of British Columbia. He chairs the Glenrose Rehabilitation Hospital Research, Innovation and Technology, and recently became the interim president of the Fusion Energy Council of Canada. He's a member of the Order of Canada, past president of the Canadian Academy of Engineering, and a CAE fellow. So Axel, you have the floor. Looking forward to your presentation.
Thank you very much, Sohail. My presentation will be run remotely, so you will hear me say click or advance the slide from time to time. Well, now for something even more futuristic than small modular reactors. And I'm of course referring to nuclear fusion. May I have the first slide, please? I would like to look at 5 question areas. What is nuclear fusion? Why is nuclear fusion important? What are the problems or what are the challenges? What's currently being done and what must be done? So as a little recap, let me go to the next slide. Thank you. On the left-hand side, in a very simplistic form, you see an example of nuclear fission, where large or heavy nuclei are split to form smaller nuclei and neutrons, and that is accompanied by energy evolution. In contrast, nuclear fusion starts with light or small nuclei and combines them to form larger nuclei and neutrons, and that also generates energy. The slide that's depicted, the image that's depicted here shows the fusion of deuterium, 2H, together with tritium, 3H, to make helium and generate a neutron. So that's essentially what fusion is, the combination of small or light nuclei that results in the evolution of energy. And if you click on it, the energy is produced because there is a change in mass. So mass is converted into energy, which is the basis of both fission and fusion reactors and reactions. An important point to note is that the products of nuclear fusion are not radioactive substances, although some radioactivity can be induced as a result of the neutrons being generated. But nuclear fusion has the inherent advantage of not creating long-lasting radioactive waste products. May I have the next slide, please? And I think it's really important to recognize that fusion is a natural phenomenon. It's a phenomenon that powers the sun. It's the phenomenon that powers actually all of the stars, where nuclei are combined, mass is converted into energy, which is then manifesting itself in terms of electromagnetic radiation. But just because fusion is a natural phenomenon doesn't mean it is easily achieved under commercial conditions or for private use. So let me take a little diversion into an analogy. And the analogy is, in fact, a human flight. Human beings have wanted to fly for a long time. They've known for a long time that flight is possible. After all, you can observe birds, butterflies, dragonflies. But that doesn't mean that it's easy for humans to fly. If you click, and since antiquity, and there's the myth of Icarus who tried to fly by sticking feathers to his arms, and that didn't work. Leonardo da Vinci in the 1400s designed a flying machine with flapping wings, thereby emulating what birds do. Then there was an excursion into lighter than air flight, principally by the French in the 1700s. But none of that really made human flight possible until the early parts of the last century, when the Wright brothers figured out that if you have the right combination of thrust that can produce lift, you can generate human flight. Their initial flight was extremely limited, no more than a few tens of meters, in fact. But they recognized the importance of lift and thrust, and they recognized that you needed a power plant in order to generate the thrust, not by flapping wings, but by turning a propeller, but having a power plant that was light enough and a fuel supply that carried enough energy in order to make flight possible. Well, you know what follows on from that, particularly during the two world wars, aircraft were developed to the point where we know them today. If in 1903 you had asked the Wright brothers, is it going to be economically feasible to fly from the east coast of the United States to the west coast of the United States based on what they demonstrated in 1903, the answer would have been, the potential is there, but it's a long way between potential and reality. So much for the analogy of human flight and fusion. Let's get back to fusion and what are the main approaches that are currently being used. The main approach that is receiving most of the attention is the combination of deuterium and tritium to form helium and a neutron. Now, deuterium exists in nature. It's part of water. We refer to it as heavy water. But tritium is not. So you actually have to produce tritium in order to make the fusion reaction work. And you do this, or one way of doing this is to take the neutron that's generated and you interact it with lithium, which makes more helium and tritium, which is what you're after. So the overall reaction is deuterium plus lithium forming helium plus energy. Now, I know we have many members here today who are from the Society of Petroleum Engineers, and most of them do not think in terms of electron volts when it comes to energy, but they think in terms of other terms. So let me translate that. And let me translate it into a simple, but what I hope is a convincing way. Imagine you take 1 kilogram of deuterium, which is obtained from water, in fact, 5 kilograms of heavy water, and you put it through the fusion cycle, which means you interacted with 3 kilograms of lithium. What does it yield? Well, it yields 300,000 megawatt hours of energy, which is actually equivalent to something like 135,000 barrels of petroleum. That's a large quantity of petroleum from 5 kilograms of water and 3 kilograms of lithium. Or if you turn it around, and we can do this on the next slide, once again, here's the overall reaction. But let's assume we have 1 million barrels of petroleum, and this is a tanker that shows carrying 1 million barrels of petroleum. That petroleum has an energy content, if we react it, of about 2.2 trillion, terawatt hours of energy. And that is the same as what you would get by reacting 7.4 kilograms of deuterium with 22 kilograms of lithium. So you can see the enormous amount of energy that can be produced by fusion using deuterium and lithium. May I have the next slide? Deuterium and lithium are not the only reagents that one can think about. In fact, there's very interesting work going on that uses boron, and boron is a naturally occurring substance in the form of borax. It has a little image inserted here of a borax mine in the Western United States. And if you react it with hydrogen or proton under the right conditions, it too forms helium. But interestingly enough, in this reaction, there are no neutrons formed. But if you look at the energy that is yielded by this reaction, it's 8.7 electron volts, as opposed to what I showed you on the previous slide. And on the left-hand side, you see the reactions of a proton with boron. It goes through carbon, and then it makes helium. And helium is an inert, non-radioactive product. So those are the fundamentals of fusion reactions. What are the challenges? May I have the next slide, please? Well, there's some really big scientific and engineering challenges in fusion. And the reason is that nuclei, which are positively charged, are resisting their combination or their fusion due to Coulomb forces. Like electrical charges repel each other. So you have to find a way of overcoming that repulsion. So how is that done? How is it done in the sun, and how is it notionally done on Earth? Well, you could do it by raising the temperature of the reagents to a very high level, like 100 million degrees Kelvin. And if you do that with deuterium and tritium, like any other reagent, it forms a plasma. That is, the electrons and the nuclei are no longer in close proximity, but they are separate. And at these high temperatures, they have a very high velocity. And when particles have a very high velocity, and they are confined so that they don't escape from each other, and when they bump into each other, they can do this under conditions where the Coulomb forces are overcome. So you have to create very high temperatures of the level that occurs in the sun, and you have to confine your plasma for the nuclei to be able to collide or bump into each other. And when those conditions are right, then the nuclei can fuse, and we refer to it as a burning plasma. So clearly, if we want to generate power, electricity, or heat, we need to be able to do this under sustained conditions. And we either have to do this in a steady state, or we have to do it repeatedly. You can think of it repeatedly if you consider the diesel engine analogy, where you produce fuel drops in an air environment, you compress them, you get the reaction, you exhaust the exhaust gases, and then you repeat it. So those are fundamentally the two basic approaches that people have been thinking about since the 1940s and 1950s to make fusion work. Raising the temperatures, confining the plasma, and enabling the plasma to burn. And the two little inserts at the bottom on the left-hand side refer to something called inertial fusion, and the right-hand side refers to something called electromagnetic confinement fusion. And I'll explain both of them a little bit more. If I may have the next slide. So in the case of inertial confinement, you start out with a pellet, similar to a droplet in a diesel engine. And imagine that this little pellet, which may be a few millimeters in diameter, is irradiated by a large number of high power laser beams in every direction, in all three directions. If that happens, the high energy from the laser beams will cause the molecules that are on the surface of the pellet to heat up, evaporate, and by Newton's simple law of reaction, action, and reaction, they will compress the remainder of the pellet. And if it's done right, the compression will be such that the temperature will approach the 100 million degree range, and a burn will result, releasing heat, helium, and neutrons. And this very conceptually is the approach that's taken, if you can click on the next one then please, at the Lawrence Livermore National Laboratory, the NIF facility. On the left-hand side, you see what's called the laser bay, where approximately 300 lasers are functioning, and the lasers impinge on a fuel pellet, which sits at the center of this large spherical reactor. And in the middle slide, you see this reactor being hoisted into place. And on the right-hand lower side, you see the inside of the reactor. And at the tip of the probe would be the fuel pellet. Now, if the laser beams are fired, clearly there's no person there and there's no crane there. But the idea is just as is shown in the diagram, of the order of 300 laser beams being focused on this little pellet, compressing it sufficiently to raise the temperature and to create and to cause the fusion to occur. This is the Lawrence Livermore approach, and it's also practiced in other places. The other approach, if I may have the next slide, is the magnetic confinement approach. as I indicated to you, a plasma consists of positively and negatively charged particles. And because they are electrically charged, you can in fact confine them by means of electrical forces. And this is done in the magnetic confinement approach to fusion energy production. And what you see here on the right-hand side is a very large facility that's currently under construction. It's the so-called ITER site. ITER stands for International Thermonuclear Experimental Reactor. It's located in southern France. It's designed to become fully operational in the mid-2030s, and it is intended to generate of the order of 500 megawatts of fusion power with an input of about 50 megawatts of input power. That's the power that you need in order to create the plasma and to confine it. On the left-hand side of this slide, you will see a cross-section of the reactor. So may I have the next slide, please? Now, where are we? I don't expect you to read the details of the graph on the left-hand side, but it has two axes. The horizontal axis shows a temperature scale, and the vertical axis, the y-axis, shows the collisional cross-sectional scale. And in order to get fusion, you have to have the right combination. The left-hand scale is referred to as a Lorentz parameter. In order to get fusion, you have to be near the top right-hand side of that graph where ignition occurs. Now, the numerous dots that you see in this slide, particularly the green ones, are showing earlier attempts, and the red ones are showing the magnetic confinement fusion attempts. And you see where ITER is located. That's what ITER is designed for. And if you look at the green dots and even the red dots, you will see that over time, we have progressed towards that yellow area where ignition occurs. On the right-hand portion of the slide, we give you some parameters. In case of the ITER facility, it's a 40-year project. It's now $25 billion plus. It's a multinational project. The US is part of it, the EU, China, Russia, Japan, Korea, India. Notably, Canada is not a member of ITER, but recently we signed a collaboration agreement with ITER, and I'll make reference to it later on. ITER is a very large facility, as the previous slide depicted. Its internal volume of the reactor is 1,000 cubic meters, and it expects to have an energy multiplier of about 10. So for 1 unit of energy in, you would get 10 units of energy out. But there are other fusion reactors in place and operational in operation. One important one is the Joint European Tokamak, abbreviated as JET. It too is a 40-year project, but it's significantly smaller, both in volume and in cost. Its volume is smaller because it actually employs much more recent and more powerful magnets than what ITER was designed for. Now, it hasn't reached a multiplier of 1, which is what you need in order to break even simply on an energy basis. But an attempt is being made this year, and it's looking very promising that you will get to 1. May I have the next slide, please? This slide summarizes fusion energy work around the world at major facilities. There's over 100 sites where fusion energy is being pursued. I mentioned Lawrence Livermore before, as well as the ITER facility and the tokamak, which is located, the JET facility, which is located in the United Kingdom. So fusion is being pursued very actively, very seriously, and collaboratively around the world, in North America and Europe, and increasingly also in Asia. Canada has two main sites at present, and if I may have the next slide, please. One of the sites is actually at General Fusion in Burnaby, Canada, which is using a combination of magnetic confinement and shock waves in order to bring about the compression. But other companies are also pursuing fusion. General Fusion is a company, it's a privately held company, unlike ITER, which is a public initiative. So Commonwealth Fusion in the Boston area is a good example of a fusion-oriented company. There's a major one in the United Kingdom as well. And Tri-Alpha is interesting because it is pursuing the boron approach, not the deuterium tritium approach. Private investment in fusion has ramped up very considerably. In total, it's estimated to approach about $1 billion of private money, which will, of course, be multiplied by public money in the years to come. So I hope this gives you a bit of an idea of what's happening right now. So if I go to the next slide, and that foreshadows what will be happening. And I take a cue from what our friends in the United States have been doing. In 2019, the National Academy of Sciences, Engineering, and Mathematics released a major report on fusion. They called it Burning Plasma Research, which then led to the publication of their most recent report, where they titled Bringing Fusion to the US Grid, where they are looking at the creation of a first-of-a-kind fusion power plant. And the idea is that this first-of-a-kind plant would be operational starting in the middle of the next decade, with an energy multiplier, of course, significantly bigger than 1. Not yet decided on what the electricity output should be, but it must be at least 50 megawatts electrical. And it should have an overnight construction cost of less than $5 or $6 billion and has an operational life of 40 years. So this demonstration plant is meant to get the US to the point where fusion power can in fact be deployed to the grid and where insights can be obtained into the design, operation, economics, and all the other issues that are related to fusion power. So if I may have the next slide, please. Now, what are the implications for Canada as far as fusion energy is concerned? One could give a talk on each one of these topics separately, but let me just highlight them. This is a new technology sector. It has its roots in existing technology, but fusion energy is a major step out from fission and, of course, from conventional energy generation. It will create many new jobs in many new areas. Just imagine, think back to what I said about lasers, electromagnets, materials, etc. Fusion will underpin electrification. That's its primary, but by no means its sole purpose. But that's largely the focus in the context of net zero by 2050. I foresee fusion and fission, for that matter, to lend impetus to the development of electrochemistry in a very major way. We can do process chemistry electrically in ways that are, in many cases, much superior to what we conventionally do. Sustainability, of course, is a major implication for Canada. And lastly, I want to mention that a major implication is for Canada's engineering, procurement, and construction companies. You know, the Stantec's, the SNC-Lavalins. Canada is very strong in this. Fusion requires enormous finances, so this is something really important for our banking sector. And never overlook the insurance sector and its implications. Nothing gets built if it isn't properly insured. Well, nothing gets built on a commercial scale if it's not properly insured. So if I may have the next slide. Before I go there, actually, I should say that we in the Fusion Energy Council of Canada are working with our partners in each one of these sectors, trying to understand the implications and taking advantage of what these implications have to offer for our country, but also for others in the world. If I may have the next slide, please. So more specifically then, what are the fusion opportunities for Canada? Well, we can build on our strengths in fusion development and deployment. And the specifics are tritium technology. Canada has very special demonstrated expertise with respect to tritium production, handling, reuse, purification, etc., which is so essential to the fusion approach that involves tritium. And Canadian nuclear labs, as well as the other Canadian operators, have very strong expertise. Material science is critical for fusion. Just think about the very high temperatures that have to be sustained. But there are also materials like electromagnets. And then there are, of course, materials that are neutron resistant. And again, Canada has considerable expertise there. We have strengths in laser technology, and we can ladder our nuclear fission expertise into the fusion area. In addition to this, we have general strengths with respect to research capabilities in universities, governmental labs, and elsewhere. And I don't want to underestimate, and I don't want us to overlook Canada's very important expertise in the EPC sector. This will be an important driver for us. And lastly, I would say the regulatory system that we have in Canada is really excellent. It's not technology specific, and it's been recognized around the world for its advantages. Now, in most cases, one talks about how to generate fusion, how to generate energy by fission or fusion or other means, but there are also major opportunities in the uses. Electrification of transportation is obvious. Resource-based industries have been mentioned. I see a great potential for fusion and fission energy when we want to diversify Canada's petroleum industry away from being primarily, or maybe exclusively, an industry that produces energy products to other products. That's a major focus of our consideration in the FECC as well. So let me conclude. First, fusion energy will be transformative globally. It's not going to be transformative in the very near future, but because it's transformative, Canada must be a major participant in its development, deployment, and use. Second, fusion energy is still evolving. It will not contribute in a major way to net zero objectives by 2050. But the net zero objectives will continue to be pursued beyond 2050. And that's where fusion will have its potentially great impact. Next slide, next point. Nuclear fusion and nuclear fission are symbiotic. There's a lot that these two energy generation forms have in common. There are also major differences, and I outlined some of them in terms of temperatures, in terms of waste products, for example. And fourth, we at the Fusion Energy Council of Canada are interested in advancing fusion in a very objective way. We see both the pluses and the minuses. We see the problems that need to be overcome, and we see the problems that need to be managed. But we also see the very, very big potential, not only for Canada, but for all the citizens of the world and for our world. Thank you very much.
Thank you, Axel, for a very comprehensive presentation. Was great looking at fusion. I think I would like to now open the floor for your questions. Please kind of use the Q&A to pose your questions. The first questions from the floor is actually with respect to aging nuclear reactors in Ontario that are being replaced by natural gas plants. So the question is why? And I'm gonna pose this question to all of you, but the person that posed the question asked Ali to answer that. So why don't we start with you, Ali, and then we go to other questions. My thoughts are that after this, we are gonna open discussion on the economics and then the regulatory and then other aspects. So go ahead.
Great. Yeah, it's a good question. So I guess in Ontario, it's important to note that there's been an incredibly large project. So Canada really has embarked on a major investment. This is a true mega project in Ontario with a decision a few years ago to proceed with refurbishing 10 out of the 19 reactors here in Ontario. These are contemporary heavy water moderated CANDU reactors. This is underway now and is running to schedule and budget and will result in Ontario's nuclear fleet continuing to run for decades to come. And really it's notable in Ontario, nuclear is a majority of the electricity supply. Typically in the range of about 60% of the electricity in Ontario comes from these plants. I would add too that Ontario Power Generation, the largest utility in Ontario, is progressing with a Darlington new nuclear project where they're planning to site a grid scale SMR at the Darlington location. I believe they are aiming for a 2028 date for deployment, and they're going to be down selecting a technology late this year. There certainly is a small percentage of natural gas use for electricity in Ontario. I think typically it's around 5 to 10%, largely peaker plants to accommodate peak generation needs through the day. That may go up and down certainly as reactors come offline for this refurbishment work. But I think that the long-term average is quite low and continues to be so.
Any other comments from Phil, yourself, or Axel?
I would certainly add a comment. We're seeing a very similar thing, probably leading on in the United States. We're finding fission reactors of the older generation aren't remaining economically competitive. And hence, as we retire them, as well as other forms of generation, such as coal-fired generation, we replace them with natural gas fired, because that's, let me call that the minimal risk position. I can make a decision today as an energy producer at minimal risk, and I'm not investing in something that now has a lifetime of 80 to 100 years. And just in terms of capital investment, it's almost the flip of nuclear. 30% of the production cost is capital, 70% is the operating fuel costs, et cetera. And it's just a flip of nuclear. So it's a minimal risk position. It's an interim position in the United States. The long-term future is unclear where we'll go with natural gas. And if I look just as an example in New England has over 60% of its electric power generation is natural gas right now. And we depend on a too small pipeline out of New York and the natural gas, liquefied natural gas facility in Boston in order to make our natural gas fired plants work. So it's an interim position. Okay.
Maybe the point I would add is that any kind of a plant that you have has a limited lifetime. At some point in time, it needs to be refurbished, upgraded, or in some cases, it has to be dismantled because it just gets to the end of its natural life. And that's something that one needs to take into account as one builds a plant. I early on mentioned that the National Academy in the United States is projecting its first of a kind plant to have a life of 40 years. So you have to think about what happens after 40 years. You might be able to string it along for another 20 or so years, but it will ultimately become obsolete technically and functionally obsolete. So it's an important consideration to take into account when one embarks on new technologies. And this is what's typically happening. I'm sure everybody in the SMR sector is thinking about what happens at the end of the life of an SMR plant. What do you do with it? What do you do with your waste products? It's an integral part of the approach that we take.
I would add one thought, Sahil, just to what has just been said, and that is in the context of decarbonization, in the markets in the United States, of which about half are so-called restructured or competitive markets, where the nuclear plants cannot really compete in any reliable manner. The benefits of clean energy production by nuclear are not recognized in the market design in the United States. Carbon-free production is not recognized as part of our market structure. Hence, nuclear was by the wayside. Natural gas doesn't pay for its carbon contribution. And hence we've got an unbalanced market situation that presumably will be resolved over time.
Well, thanks. I think, actually this really kind of maybe lead to this discussion of economics of the future would be most likely electrification. And there are maybe two scenarios. One is super grid, the other is expanded grid. So with those scenarios, Phil, what is the most cost or what is the low hanging fruit nuclear technology that can really help?
Well, I think in terms of level of maturity, okay, we have two primary choices today in level of maturity. Something that is light water based, whether it's a large reactor or a small modular reactor, or a high temperature gas reactor technology. Again, size may vary depending on the application. Those are the two that we have the most experience with today and provide us a lower temperature reactor, 300 degrees Celsius or so in the light water reactor world, and upwards of 800 degrees Celsius in the high temperature gas reactor world. Those are the most mature. Those are the ones that are closest to off the shelf. Shortly, right behind those is the sodium cooled reactor capability of the GE Hitachi design, which is somewhat less mature, but similar maturity to the high temperature gas reactor. Those are the options available in the nuclear energy world that have been brought to maturation, have been close to commercialization or commercialized, depending on the specific design, and are available and more closely off the shelf. All right, that's where we are today. All right, the other designs, the other technology concepts are all sitting there with various levels of technology maturity, more or less challenges, more or less economic challenges.
Thanks, Phil. So what about, Ali, what about SMR in terms of low-hanging fruit? We hear that many technology providers are exaggerating the cost of SMR and are saying it's extremely economic, but it's untested. So realistically, what do we expect?
Yeah, so I guess it's important to remember the three different streams that I talked about when we talk about SMRs, and the
Right.
first being the on-grid replacements. These do have to be extremely competitive on economics, certainly. And I think part of any initial demonstration project is essentially critically going to try to prove that out. So that's a key component. They won't really come forward to fruition without that sort of key economics piece. It's a driver centrally to all of them. But important to note, the advanced reactors that are further out in development, they bring a lot of promise through simplifying the systems, using different coolants. These are technologies that require further research, but could be a game changer in terms of overall economics. And that's kind of hanging out there in a 10 plus year time frame. But the third category, these micro reactors, they could be really valuable in some scenarios that it doesn't make sense to run many hundreds of kilometers of high voltage power lines, for example. And it makes more sense to implement a small modular reactor. Today, many of these mine sites, for example, run on diesel power. And so the price point to be competitive is much higher. So you'd be talking potentially 10 times the price of what we pay on grid for electricity today. And in those sorts of environments, a microreactor that's designed for that sort of system could be very competitive, and that's what they're talking about. And again, first step is a demonstration, and that's why CNL has established this demonstration call for open invitation for demonstrations, and sort of are setting ourselves up to invite those vendors to prove out those designs. It is a strategy by Canada to not select a winner. So we're not designing an SMR by the sort of federal government. This is very much an open arena for vendors to compete and bring their technology to bear. So I think that's obviously a central component is proving out, can you build this for the costs that you advertise?
Yeah, well, thanks. And Axel, supposedly fusion is going to become reality, say, in 20 years or so. What is the expected cost? How is this going to compete with other sources of energy, in your opinion? Has there been any study done to kind of understand the economics of it?
Well, some preliminary studies have been done, and some you can actually infer. If you look at the first of a kind plant that the National Academy is recommending, and if you go with $5 billion and 50 or 100 megawatt, you can actually calculate, and 40 years lifetime, you can start to estimate what the levelized cost of electricity is. And it's in the 30 to 40 cents per kilowatt hour range, which is clearly not where you want to be if you want to be competitive.
That's right.
But that's why I was saying, if you look at the Wright brothers in their plane in 1903 and you ask them, what's it going to cost to fly from North Carolina to Los Angeles with your contraption, you wouldn't have been able to arrive at a realistic figure. So I think it's pretty clear where we need to be. And I give you my subjective goal, and that is we have to really get towards 1 cent per kilowatt hour of levelized cost of electricity. Can we get there? That's another matter. But I think we have to have a target of that nature in mind. If you say it has to be 10 cents per kilowatt hour, that's fine too. But we have to be realistic in order to achieve that. And I don't think we can just count on the carbon tax on natural gas or coal or biomass to compensate for it. So I think these have to be good cost estimates, and we are not there yet. I think once we demonstrate fusion under sustained conditions at ITER or in the United Kingdom, we will be getting much closer to having realistic figures. But I have no doubt that the potential is there.
Right, thanks. So there are a few questions from the floor. I'm going to read them. The first one is about CANDUs have long been seen as a way of powering lower carbon heavy oil and carbon-based product production. Do you envision that the Alberta government and major OPCOs overcoming their reluctance to engage? Who would like to respond to this question?
So I can give a comment on that. From
Right.
my perspective, I know CANDUs have been considered in the past with various
Right.
studies performed in Alberta. And I think that the key point of all those studies were that the capital cost of a contemporary, conventional larger reactor was very high, and it made the overall project uncompetitive on economics. That said, the shift here to SMRs and taking into account carbon taxes, we're in a different paradigm. So at CNL, we've done some hybrid energy system modeling and produced very similar graphs to the ones that Philip presented in the case study that show that certain SMR designs might be well suited with high temperature process heat for these types of applications. And when you include carbon taxes in the mix, you have to really reevaluate those economics. $170 per ton, which is what's been publicized and we're moving towards by 2030. This does shift the equation substantially.
Yeah, and maybe I should confirm, actually, Phil was saying that we should take a look at economics of high temperature gas reactors, because when we did that estimation, essentially what it came down, it would be like if we have a $60 per ton of CO2 cost with the current natural gas price, it seemed that it would be economic. Of course, we have many challenges. It's technologies, it would take a long time for getting it licensed. There is the cost of overrun that we have had in Alberta. The regulatory system is not familiar with it. There are lots of challenges, but economically, that was around $60 per ton of CO2 tax that would also make it economic. But that's a very rough calculation anyway. So any other comments on this question, or do we want me to go to the next question? So thank you, Ali, actually, for answering it. There is a comment about the previous question that in Ontario, actually they are talking about NGC will stop operations in 2024/2025, and Ontario is expecting that this capacity of 30 GWE will be replaced largely by natural gas, and Ontario needs to rethink the strategy. Just a comment. And next one is about really when you put a diversification of SMR, solar, wind, all of these other things together, you combine them. Can we just avoid grid upgrades, or do we still need to increase grid upgrade? I think really the question in my mind is, if we want to go with super grid, then these large reactors would make sense. But maybe there is a kind of a cheaper way of going about it by just mending it through SMR and other things along the way. What are your thoughts? Which one would make more sense? Phil, would you like to take that question?
Yeah, I think the thought of one, diversifying is extremely important. Two, going to the smaller reactor size provides you greater flexibility in what you do with the grid. I know if I reflect on the United States, our grid is very large across the country. In the east, it's highly interconnected, and the west is highly interconnected. But we saw what could happen in the recent experience in Texas in the cold weather when you have a smaller grid and without interconnections to the larger grid, and it finds itself in deep trouble very quickly. So I think small reactors, diversified sources of power is a good way to look at the options for avoiding upgrades to your grid in the near term. I think that's a possible course that will be looked at very carefully.
And would you consider like SMR as generating hydrogen and storing hydrogen to generate electricity? Is this an option for kind of overcoming the fluctuations in terms of power demand?
Yes, very much so. Okay, I think that and looking at that seriously, I think depending on what type of SMR, that becomes more economically credible to do a hydrogen production, for instance, as a alternative to a straight electricity production and using some kind of hybrid thought process. I think the small modular reactor is a particularly, whether it's light water reactor or non-light water reactor based, it provides a good opportunity to look at our grids differently than we do currently today.
Any other thoughts, Axel? Go ahead.
Yeah, a couple of thoughts. I think in all of these applications, because the demand varies, one really wants to look at turn down capabilities. You design the reactor for a certain capacity, but by how much can you turn it down before it really doesn't function properly anymore or economically? Storage then becomes an obvious, and hydrogen was mentioned. But there are some ways of actually using excess electricity when it's not used for the primary customer without storage. One of them is actually food production. If you think about lighting of greenhouses, if they are lit at night when there isn't a demand, then that's a good use of the electricity. I think CNL gave a presentation not long ago about SMRs in a community like Iqaluit. And the question was, what would be the right size of an SMR for a small community like Iqaluit in light of the turn down capability? And hydrogen storage is potentially possible. It will add significantly to the capital cost if you were to do this. But if you can find another intermittent use, like food production, that opens up other opportunities, which I think are quite interesting.
I think the concept, Axel, that you're mentioning, and I'll just generalize it by saying hybrid energy systems,
Yes.
in doing so, technologically, the path is a lot straighter, if you will, to achieving success there. The economics are straightforward, but the business model is a problem that we're struggling with in the United States. Who owns all of those entities, if you will, and how do you adequately share in the return on investment? And that's where we're struggling right now to find a way to make that work.
Yeah, and what a business sector doesn't know, it's very cautious about.
Yes, sir.
And partnerships are great, but partnerships can also be problematic.
So
we all want our return on investment.
Yeah, exactly. Yeah.
So Phil, there's a question for you because you are expert in submarine and nuclear submarine. Is there potential to take decommissioned nuclear submarine as an SMR at remote coastal location and then use it essentially? I mean, I know that those are actually extremely expensive when they were put together.
Yeah, the options exist. That's been looked at in the past, in particular with aircraft carriers, which have large capacity for electric power generation if we so wish to do it. The economics they're difficult. Let me just put it that way. The economics are very difficult. All right. And if I might, without getting into any detail at all, if I might, we did not design the power plants or propulsion plants rather, in our nuclear Navy to operate long-term at shore. Okay, the considerations of military necessity and how you look at the safety case is different than we would for a commercial reactor. So I would hesitate in a very practical way of operating a naval nuclear plant that you've decided you can economically do because the government's paid for it already. From a safety standpoint, I wouldn't do that. Okay, we typically, just so you're aware, we typically don't operate our submarines except for short periods in ports, and that's done intentionally. Okay.
Sounds great. We are coming to kind of to the closing part of our presentations. As I asked at the beginning, I think we want the concluding remarks around 1 minute or so from each of you before we close the session. So now why don't we start, Phil, with yourself, with your concluding remarks.
Okay.
And then next would be Ali and then Axel.
All right. Well, let me reiterate from the concluding slide that I had in my presentation that nuclear energy does provide a compelling option for clean and reliable energy production. And I fully expect that it's going to play an essential role in achieving an economic net zero emissions future. It will play an essential role. Overcoming the challenges of demonstrated competitive economics and high-level nuclear waste disposition, they must be overcome to have a future success in nuclear energy systems. Technological success paths exist for both. However, the political and societal acceptance of the waste disposition path is unresolved. They're promising first steps, at least in the United States, on interim storage, but we haven't solved the political problem at this stage. A diverse energy production portfolio is central to managing long-term business risk for electric power generation rather, and that goes along with what Axel mentioned earlier. Nuclear energy as a component of such diverse portfolio has consistently been shown to provide the most economic results, and Ali mentioned that when he was speaking. I am optimistic regarding a sustainable future for nuclear energy. Multiple paths to exist from advanced LWRs to non-LWR technologies of various sizes and for a broad range of applications. Energy producers will decide which of these technologies should be matured. The bottom line is economics rule, and nuclear energy right now has a credibility gap in demonstrating that it can be made economically competitive over the long term. We have to close that gap. Thank you.
Thank you. Yeah, that was a great conclusion. Ali, how about yourself?
Yeah, sure. Thanks very much, and excellent discussion. Thank you so much for inviting me. In the face of existential threats of climate change, Canada is certainly investing in the full suite of energy technologies to reach these net zero emission goals. And nuclear energy is a really important part of achieving these objectives. And so, we certainly see tremendous potential to expand the use of safe nuclear technologies, whether it be fission in the near term and SMRs, and ultimately fusion technologies in the future, both here in Canada with real applications and around the world. And so I think Canada's well positioned to be a partner with other leading nations right at the forefront of this technology, and then do the hard work of demonstrating it and proving out those economic questions.
Thank you, Ali. Axel, how about yourself?
Very much agree with what has been said, and I don't want to repeat it, but I would like to focus attention on the importance of Canadians to become more familiar and knowledgeable about fission and fusion energy, both their potential, their realities, and their challenges. And I very much like to encourage government and industry and our universities to also take the long-term approach to energy generation and utilization. That's not to say we shouldn't look at the short term, of course we should, but not exclusively to the short term. So I think this coordinated longer term approach would serve us well in our country, and if a similar approach is taken by other nations collaboratively with us, it will serve everybody very well. Thank you.
Well, thank you very much, Axel. And what I'm getting actually, the several texts, etc. That was great presentations, great discussions. Really appreciate your work. And I think also I want to thank the organizers, the CAE, SPE, PTAC for doing this, putting it together. So thank you all. And, you know, I think looking at the future, this business of nuclear is going to definitely play a major role. So we really need to kind of continue our collaboration and working together. Again, I believe that we are working in terms of some of the pathways to net zero. We got to consider always nuclear is going to be a very major area to be considered. So thank you and appreciate for your work. Have a great day.
Thank you.
Thank you very much.
Thank you.
Thanks, everyone. Great work today.